Well, good evening, ladies and gentlemen. For those who don't know me, I'm Alistair Burt. I'm the Executive Dean of the Faculty of Health Sciences, and I'm delighted to welcome you this evening. I'd like to start by acknowledging the Kaurna people, the original custodians of the Adelaide Plains and the land on which the university's campuses at North Terrace, Waite, Theberton and Roseworthy are built. So thank you for coming along to the latest Executive Dean's public lecture. And tonight I'm delighted to introduce Professor Amanda Page, who heads the vagal afferent research group within the Centre for Nutrition and Gastrointestinal Diseases at the university here. Amanda obtained her first degree, an honours degree in pharmacology at Liverpool University before moving to London, where she got her PhD at UCL. She then moved to Adelaide to work initially in the Royal Adelaide Hospital and was involved in industrial collaboration with AstraZeneca, a very successful partnership which resulted in some significant drug development programs and patents. Then she moved to join us in the University of Adelaide, and last year she was promoted to the level of professor, a very important recognition of the work that she'd done with us. And essentially tonight, I guess, is like her inaugural chair lecture. She is a leading authority on vagal innervation of the gut and how this relates to major disease. Now, vagal there refers to the vagus nerve, which is a really important sensory regulator of the gut, something that when I was a medical student was even more prominent, I guess, than it is nowadays in, say, surgery, because of the vagus nerve was the one that they all cut to try and cure peptic ulcers, which we now know isn't really the way that we need to do that. Anyway, that is how I first got to know the vagus nerve, was holding a retractor for various surgeons as a medical student. Anyway, Amanda is using innovative approaches highlighting the importance of the stomach in the regulation of food intake. Her topic this evening on the gut and appetite regulation in health and obesity will present a very interesting discussion on how a more comprehensive understanding of the mechanisms involved in vagal afferent signaling will enable more effective drug therapies and or lifestyle strategies for the treatment of obesity. So can I then now welcome Professor Amanda Page. Thank you.
Can everybody hear me before I start? Well, thank you, Alistair, for a wonderful introduction. There's nothing more to say. I can go home now. As Alistair said, I'm going to be talking about the gut and appetite regulation in health and obesity, or maybe more relevant to my research, the stomach as a target for obesity. So I'm going to cover obesity and the current treatment options, and then I'm going to go straight down to my favourite topic, which is peripheral appetite regulation. And this will be there will be particular emphasis on those vagal afferent nerves that innervate the gastrointestinal tract. I'll show you that they are not a static, they don't respond in a static manner, and they show circadian variation, so they respond differently over a 24-hour period. They can be influenced by food intake status, such as, and there's differences in response in fed and fasted states. And then I'll show you the effect of appetite hormones that circulate in the blood and are also produced in the stomach and small intestine that can affect these vagal afferents. Then I'll go on to what happens to these vagal afferents in obesity and show you what happens if we reverse that obesity and put them back onto a normal diet. So, as I said, I'm going to talk about obesity first, and this is a diagram showing the rates of obesity in 2014 globally. And you can see here that in America and the UK, Australia and New Zealand, the rates are greater than 25%, which is quite alarming. And this is quite nice. This is taken from Google Images. But you can see this is the obesity rates by country reported in 2013. You can see that the USA is the most obese at about 34%, and Australia is not far behind actually, about 25%, close to the UK. And then there's Japan, which has a very small obesity rate of 3%. But even in all of these countries, the rate's increasing. And perhaps that's the major concern, actually, that the obesity trends are quite dramatic. And you can see this is the trends in the United States of America, in the different states, from 1990 through to 2009. And you can see that just in 9 years, the obesity rates go from about 10 to 14%, up to, in these southern states, as high as 20 to 24%. And then by 2009, in these southern states, it's greater than 30%. This state here, you might be interested, is actually Colorado. And in Colorado, they have a more active lifestyle. They're outside, they're cycling, they're walking, they're hiking, and it's kept the rates of obesity down, but even in this state, it's increasing dramatically, and it will soon catch up with the rest. It's predicted that by 2030, 86% of adults will be overweight and 51% will be obese. And just to show you, the trends are pretty similar in Australia, actually, perhaps a bit more dramatic. This is the rates of obesity in Australia in 2007, 2008. You can see that New South Wales and Western Australia have a rate of 25 to 30%. But by 2011 and 2012, don't quite know what's happened to Queensland, but its obesity rates are at 30 to 35%. So why do we care if people get obese? And it's mainly because of the diseases that are associated with obesity. And there are numerous diseases such that actually obesity is the major health factor. Now it's overtaken smoking and heart disease. And these diseases include diabetes, which is a major concern, type 2 diabetes. There's heart disease and high blood pressure. Then there's diseases that are associated with the actual amount of mass of fat, such as gastroesophageal reflux disease and sleep apnea. And then there's certain types of cancer that are linked to obesity. So it's a major risk factor for many diseases. And this is just a meta-analysis of various studies looking at the rates of obesity the rates of diabetes in obesity, so the relative risk of diabetes. And there's over 20 studies here, and it's come out with a figure that the risk factor for type 2 diabetes is about 7 times that of normal lean people. So what are the causes of obesity? You might simply think that it's a matter of eating too much and not doing enough exercise, and that certainly is a factor. We do live in a very inactive society. We spend a lot of time at computers. We spend a lot of time viewing the TV. We don't get out as much as we should do. But there are a number of other factors that affect that can cause obesity. So certain viruses can alter our metabolism. Hormones can affect metabolism, even peer pressure. So when you're at work and you're offered a cake for someone's birthday, this can influence your body metabolism. There's things such as stress, and we do live in a very stressful society that can affect food intake. Pollution, sleep, and I'll show you some circadian studies, but shift workers are significantly more prone to obesity than people that work from 9 to 5, and which is quite important in Australia because over 16% of Australians are shift workers. And then there's obviously food abundance. We don't have to go hunting or gathering food anymore. We can just drive up to the window in the McDonald's and get food. So there's a lot of factors that can cause obesity. So what are the treatment options? Well, there's obviously lifestyle modifications. We can eat less food and exercise more, and you can certainly see that here, if we ate this burger, we'd have to run a few marathons to burn it off. Unfortunately, the success rate for this type of lifestyle modifications is very low, and you have to monitor the food intake and the exercise that you're doing almost continually if you were obese and you've lost weight. Then there's pharmacotherapy, and there's an array of drugs that are on the market for the treatment of obesity. There's this one, Xenocol, which is a lipase inhibitor. It prevents the absorption of fat, and as a consequence, that fat just leaves the body, so you have quite often diarrhea. Then there's a few drugs that act centrally on specific appetite sites in the hypothalamus, which are appetite regulatory. And again, you have a plethora of side effects. Oops. So actually the best treatment for obesity is actually bariatric surgery. Unfortunately, bariatric surgery is only an option really if you're severely obese. It is an economic strain on the country. The country certainly couldn't afford to provide bariatric surgery for all obese individuals. And then there's also the complications of quite invasive surgery procedures, and some of these procedures are lifelong. So you have to really want this to occur to go through it. But there's actually two main types. There's the restrictive surgery, and this includes gastric band and sleeve gastrectomy. So you can put a band around here, which restricts the amount of food going into the stomach. Or there is surgery where you actually take away this outer curvature of the stomach, so it reduces the size of the stomach. And then there's restrictive and malabsorptive, and this takes the form of Roux-en-Y gastric bypass. So actually you cut the stomach, make a smaller pouch, and then you bring the intestine back up so that you bypass the stomach and upper half of the small intestine completely. And this obviously reduces digestion, and you don't absorb as much food. So this is the actual, as I said, the best treatment for obesity, and it may give us an idea of where we can target new pharmacotherapies. And as it's in the stomach and small intestine, maybe we should be looking at treatments that control appetite signals from the upper gut. And that's where my research comes into effect. So within the stomach and small intestine, there's two main mechanisms of satiety signaling. And these form in the stomach. It's more of a response to mechanical stimuli. So as food enters the stomach expands and the wall stretches, and this activates nerves in the stomach, which then sends signals up to central areas where it's processed, and ultimately leads to feelings of satiety, and if we eat too much, nausea. And then in the small intestine, it's more of an enteroendocrine response to nutrient. So the nutrient acts on specific sites on the surface of specialized cells, where it initiates intracellular processes that ultimately lead to the release of a transmitter, and in this case I've just said cholecystokinin. And then this transmitter or hormone, peptide, can either enter the circulation where it makes its way up to the brain, or it actually activates these vagal afferents and gets up to the brain a lot quicker. This is some figures that Richard Young, who also works within the Centre of Nutrition and Gastrointestinal Diseases, has provided for me, and he's interested in sweet taste within the small intestine, and he's shown quite nicely that these sweet Glucose, for instance, can activate specific sites on these cells that cause release of a transmitter. So if we look at this in detail, we can see that the glucose acts on this specific site, which is a sweet taste receptor. This initiates an intracellular process, which leads to the release of a transmitter. He's also provided these beautiful images which show localization of a component of that sweet taste receptor and the peptide GLP-1, and you can see that they're co-localized on this composite form in the same cell. So you can see how the process works. So there's not just sweet taste receptors, and I'm just going to briefly show you this. There's a number of receptors along the length, so this is from the stomach through to the colon. There's a number of receptors that are expressed in the gastrointestinal tract to different degrees. This is the expression of sweet taste receptor. You can see that it peaks in the small intestine, and there's also bile receptors. There's a number of amino acid receptors that detect the components of protein, and then there's also a number of fatty acid receptors. So there's actually quite a few taste molecule signals within the gastrointestinal tract. It's not just confined to the mouth. And these signals all provide information that will control either appetite, motility along the gut, or absorption, depending on their role. But as I said, I'm quite interested, and we'll go back to my favourite subject, these mechanosensitive afferents in the stomach. And this is an image taken from a paper by Paoli et al., and it shows the branching of these tension-sensitive afferents within the stomach wall. You can see that their anatomy is perfect for detecting a distension of that stomach wall. And we can also record from these afferents, and you can see this is a typical tension receptor response to tension, and you can see that it's got a basal activity, so these are actual action potentials that are going along this nerve, and you can see that when stretch is applied, you get an increase in the intensity of these action potentials, and it's this increase in intensity that tells the central areas that the stomach's full. So when I first arrived in Adelaide 21 years ago, I spent a lot of time developing a preparation that allows us to record from single vagal afferent fibres. And to do this, what we do is we take out, at that stage it was actually ferrets, because ferrets have gastroesophageal reflux disease and mice don't, but we now use mice. We take out the stomach and esophagus, as shown here. We open it up longitudinally and we pin it out flat in this chamber here with the mucosa, or the lumen of the luminal surface, facing upwards. And then we perfuse with a Krebs solution, and this is made up of different salts. It maintains viability of the preparation. It allows us to record from the nerves that innervate that stomach for up to 6 or 7 hours without changes in the viability. We then take the vagal nerves, or the sensory nerves, through into a second paraffin-filled chamber, and that paraffin oil provides electrical isolation, because what we're recording from is electrical signals along that nerve. And then they've got a nice sheath on them, we desheath them, it's like taking a pair of tights off, and then we split that nerve bundle, and remember it's a mouse, into about 14 or 16 smaller bundles. And then we place one of those bundles, one at a time, onto a recording electrode. Then we can look for mechanically sensitive afferents by brushing over the surface of the stomach. And once we've found something that responds to a mechanical stimuli, so once we see action potentials, we can use more refined mechanical stimuli in the form of calibrated von Frey hairs, so we can actually stroke over the surface of the mechanosensitive region, or we can apply a stretch stimuli, so we can attach a claw adjacent to the receptive field, which we can connect to a cantilever system upon which we can place weights. So using this preparation, we found two types of mechanosensitive afferent in the stomach. There's ones that we've termed mucosal afferents, and these respond to mucosal stroking as low as 10 milligram von Frey hair. And at 10 milligram, you can barely feel it on the palm of your hands, so it's very sensitive. And you can see here that what you get is action potentials generated every time the von Frey goes over the receptive field. In contrast, these mucosal afferents don't respond to stretch even as high as 5 grams, and 5 grams is quite severe for a mouse stomach. But you can see that there's little spikes, action potentials at the beginning and end of the stimulus, and this is because the mucosal afferents are that sensitive, they respond to the movement involved in the stretch. They don't respond to the stretch stimuli, but they'll respond to that movement. So these afferents are thought, and there's no direct evidence yet, to be involved in discrimination of particle size, and then giving negative feedback onto the control of gastric emptying. So they won't let gastric emptying occur until the food is churned enough not to activate them. And then there's the tension-sensitive afferents, which also respond to 10 milligram von Frey hair, but unlike the mucosal ones, they give a nice graded response to stretch, as you can see. So this is 0.5 grams up to 5, and you can see the response gets progressively bigger. And these are the ones that you classically think of as signalling fullness to the CNS. So I suppose one of the questions is are these responses to mechanical stimulation static? So if we apply a 3 gram tension to that vagal afferent, will it always give the same response, or is it modulated in some way? We've been spending a few years addressing this issue. And we have an NHMRC grant looking at circadian variation in these gastric afferents. And we know that the circadian clock influences nearly all aspects of physiology and behaviour, not just the sleep-wake cycle, but the endocrine system, body temperature, gastrointestinal tract, and hepatic metabolism. And I'm just going to briefly go over, I'm not going to go into it in detail, but basically there's a master clock that's found centrally within the suprachiasmatic nucleus, and this has input from the eyes, so that it is aware of the light-dark cycle when the sun's rising and falling. And this master clock then controls what are known as slave clocks in the peripheries. And two typical slave clocks are the liver and the kidneys. And this control is either neuronal, by the autonomic nervous system, or through the release of corticoids and ACTH into the bloodstream. You can see that in addition to the suprachiasmatic nucleus, there are influences with food intake, the amount of activity we do, and body temperature that can influence those circadian rhythms. So our thought is, what do the gastric afferents, do those sensory nerves that innervate the stomach show a circadian rhythm? And there are some clues. We know that food intake is greater at particular times of the day, and this is true of rodents and humans. And remember that rodents are actually nocturnal, so they have an opposite food intake pattern to humans. But this is the stomach content in mice taken at several times at 3-hourly intervals through a 24-hour period. And you can see that the amount of food in the stomach varies depending on the time of day. So in the daytime, when they're docile and asleep, there's not much food in the stomach, they're not eating much, and at night time you get a peak in food intake. In fact, when you take the stomachs, they're completely bloated and stretched. So there are links with energy regulation and the circadian clock, which raises the possibility that the timing of food intake may play a role in weight gain. And as I've said to you, disruption of circadian rhythm, for example in shift work, is associated with a higher risk of being overweight or obese. And 16% of the Australian population are shift workers, so this is quite an important factor for Australian health. So we did decide quite painstakingly to do some electrophysiology, so we used that preparation that I showed you where we put the stomach and esophagus in organ bath, and this was every 3 hours from 6 a.m. through to 3 a.m. and we recorded from those nerves the response to stretch and the response to tension. So this is and the response to mucosal stroking, and so this is the response to stretch, and you can see that if we record from those afferents at different times of the day, we actually get a circadian response. So this is actually the number of impulses or action potentials generated per second to a 3-gram stimulus. And you can see that in the daytime, when they're docile, the response is much higher than at night when they're active and need energy. And if we superimpose the stomach content that I just showed you, you can see that the stomach content, when the afferent activity or the sensory activity is high, the response to stretch is high, the food content is low. So that response is preventing the intake of much food. Whereas at night, when they need energy, the response to 3 grams tension is low, so the signal for satiety is low, and so they can consume more food before they get that higher signal. So I've shown you that they respond in a circadian manner. What about under different energy requirements? What happens if they need energy, if they've just been fasted and they're not in a situation where they've got easy access to food? So this is gastric satiety signals under different conditions of dietary demand, and it's specifically looking at fasting. And what we have here is in the blue is the response to mucosal stroking in fed animals, fed ad libitum, and in the red is animals that have been fasted for 18 hours. So they need energy. And you can see with the mucosal stroking, this is impulses or action potentials generated per stroke. There's not much difference between the two. However, with the tension receptors, in the fed animals, you get this nice graded response to tension. And when you fast them for 18 hours, it's significantly dampened. So when they need energy, the response of those tension receptors is dramatically reduced, and they're able to take in more food. And then there's the question of appetite hormones. I mean, the body, hormones are circulating through the body continually. What effect do these hormones have on these sensory nerves? The appetite hormones that I've been concentrating on are actually found within specific cells within the gastric mucosa. So here we have cells that contain leptin, which is a satiety hormone. It makes us feel full. And there's also cells that contain ghrelin. Ghrelin is a hunger hormone, and it's produced mainly in the stomach. And you can see if these hormones are released from these cells, these vagal nerve endings, these sensory endings, are ideally positioned to be affected by them. I'll just give you a little bit of anatomy. So the cell bodies of these vagal nerves are found in the nodose ganglia, and they're not the only. So the ones innervating the stomach and small intestine are not the only cell bodies in this nodose ganglia. All of the vagal nerves have their cell bodies here, So that's nerves that innervate the lungs, the liver and the heart are all in here. And then they terminate in the CNS. So I'll start to talk about the satiety hormone leptin first. And the main source of leptin is actually from adipose tissue, so fat cells themselves. And as the fat cell increases, you get an increase in leptin, which ultimately makes its way to the hypothalamus, that area in the brain that controls appetite, where it reduces food intake and it increases energy expenditure. If we lose fat mass, the opposite occurs. We get a decrease in leptin, which increases food intake and decreases energy expenditure. And you can see that the fat plays an important role in the long-term control of body homeostasis. And the importance of leptin can be clearly shown in these mice. This is a mouse that has no leptin, so it's a leptin knockout mouse, and you can see if there's no leptin, it actually becomes obese. It's hyperphagic, it eats a lot from birth, and it becomes obese. And the same for the protein, the leptin receptor that leptin actually acts on. If you knock out that receptor in mice, again they become hyperphagic, and they gain considerable amount of weight compared to the control mice. So this receptor is very important in the control. This hormone is very important in the control of food intake. And this is not just in mice. There are conditions where there's leptin deficiency in humans, and this is a 3-year-old who weighs 42 kilos due to a leptin deficiency, and you can see he's quite obese. And if you treat these individuals who have this deficiency with leptin, then they will lose weight. So if we go back to the leptin and the stomach and those sensory nerves, we know that it's present in the stomach. We know that the receptors, or the site that that leptin acts on, is present in the nerves that innervate the stomach. So with this receptor here. And we know that leptin-positive cells are close to vagal afferents. So the green on this image are leptin, the cells that are marked up for leptin in the stomach. And this red is actually a vagal afferent nerve coming down quite close to this leptin-positive cell. So what effect does leptin have on these nerves? In mucosal receptors, those are the ones that respond to mucosal stroking, this is mucosal receptors from mice that are fed ad libitum. You can see there's a nice graded response to mucosal stroking with the von Ferry hair. And as you add leptin, increase in concentrations, you can see that it really does significantly increase the response to stroking. However, if you fast the mice for 14 hours in this case, that effect of leptin is completely abolished. So the effect of leptin on these sensory nerves really does depend on the nutritional status. In the attention receptors, in mice that are fed ad libitum, leptin has no effect on the mechanosensitivity or those responses to stretch. But if we fast the mice for 14 hours, then we get a significant reduction in the mechanosensitivity to stretch, which suggests that the leptin actually has a dual role in the control of appetite signals from the stomach. In that, in fed animals, it has a satiety effect, but if energy is required, it can switch and reduce the mechanosensitivity of those afferents to allow more food to be taken in. So we can go from an anorexic effect to an orexigenic to encourage food intake. Then there's the hormone ghrelin, the hunger hormone. And as I stated, this is produced almost exclusively in the stomach. And again, this hormone can either enter the circulation and make its way up to the brain and the appetite areas, or it can act directly on these sensory nerves. And again, here we've got some images showing some ghrelin positive cells within the stomach wall and a vagal afferent nerve coming quite close to those cells. So with ghrelin, the story is slightly different in that this is the response of mucosal receptors to the stroking, the fine stroking. Ghrelin has no effect in mice that are fed ad libitum. But if you fast them for 14 hours, then it significantly reduces the response to mucosal stroking. On the tension receptors, even in fed animals, ghrelin is quite a powerful hormone and will increase the ability to eat more food. So even in fed animals, you get a reduction in the mechanosensitivity of those stretch receptors, so a reduction in the signal up to the CNS saying how full you are. And after 14 hours, you still get a reduction in mechanosensitivity. If not, it's a little bit more enhanced. So the take-home message one is that gastric satiety signals exhibit a high degree of plasticity to finely control the amount of food consumed. These satiety signals can change in response to circadian cues, energy demands. So if we've not eaten for a few hours, then the mechanosensitivity of those nerves will change, and exposure to appetite hormones. So I suppose the next question is, what happens in obesity, and are the changes reversible? So we have a mouse model of obesity, and here we have two sets of mice. The ones in red are fed a normal standard chow in the facility, which is about 12% energy from fat, and then these mice have been fed a high-fat diet, which is about 60% energy from fat. It's a lard-based diet. It's actually quite tasty to begin with. It tastes a little bit like shortbread, so the mice like it. It has that aftertaste of lard, which isn't too good, but they seem to love it. But you can see that they gain significantly more weight than the ones on the normal chow. And actually, their abdominal fat, they've got considerably more abdominal fat at the end of that period than the normal chow mice. So if we compare the mechanosensitivity of those mucosal afferents between standard laboratory diet and the high-fat diet, you can see there's actually no effect. So there's no effect on those mucosal responses to mucosal stroking. However, if we have a look at the response to tension, so this is in the standard laboratory diet, we get a nice graded response to tension from 0.5 to 5 grams. If we feed the mice, even actually, I mean, these are 24-week studies, but if we just feed them for 12 weeks, we still get the same. We get a significant dampening in that response to stretch. So those signals to the brain saying that the stomach's full are significantly reduced by greater than 50%. And this doesn't just occur in the stomach. Michael Bayek in Canada has shown that you get this same reduction in response to distension in jejunal afferents, that's small intestinal nerves. And you also get a reduction in the response to some of the hormones that are released from the small intestine, including the response to cholecystokinin. So it seems to be a theme that goes through the gut. Oops. So, obviously these experiments are all done at one time point. So what we need to establish is if you get that dampened response throughout the circadian rhythm. And that's exactly what we've done. We're gluttons for punishment, so we're in summary on doing experiments at 3 o'clock in the morning. And you can see that here, these are the mice that have been fed a standard laboratory diet. You get this nice circadian response to stretch, the 3 gram stretch. And in the high-fat diet mice, it's basically a flat line. There's no change in the mechanosensitivity of these afferents. So you can see that actually the responses at night when they're usually feeding are not not really that different. But the responses in the daytime, when they shouldn't be feeding that much because they don't need the energy, because they're docile, they should be asleep, is dampened. So it's those heightened responses to stretch that stop us eating too much when we don't need the energy that are affected. So we're quite fortunate in SAMRI. This is a combined funded core facility. So it's partly funded by the University of Adelaide, partly funded by SAMRI, and then the NHMRC gave a significant amount as well. We have these metabolic monitoring systems. We've actually got 16 of these cages. And these allow us to measure not just activity around the cage, but also the amount, the frequency and the duration of the meals that the mice are eating. So these little squares here, these are little mass monitors. And we put the food hopper and the water hopper onto these mass monitors, and we can monitor instantaneously what the mice are eating, how much they're eating, what they're drinking, how much they're drinking. And this third one here is like a little house that they can go into and sleep. Every time they go in there, the mice are weighed. And then there's airflow through here, which allows us to look at the respiratory quotient, how much energy they're using. And then we haven't used this option yet, but we can put a wheel in the cage and look at wheel movement as well. So we can monitor how much they're moving around the cage and also how much they use the wheel. It's a very expensive luxury home for the mouse at about 15k a cage. But it does give an abundance of information on the behaviour of these mice. And I'm just going to show you the information on meal size that we've obtained from these mice in these different groups. So this is light phase, dark phase, light phase, dark phase. In the standard laboratory diet mice that have been fed ad libitum, you can see that in the dark phase, when the mechanosensitive, the responses to stress are dampened, you actually get an increase in meal size. Whereas in the light phase, when the sensitivity of these afferents is at their peak, the meal size is reduced. However, in the high-fat diet group, where there's no difference in the mechanosensitivity of the afferents, there's no difference in meal size either. So the next question is, what's causing this dampened response? And there's some indication in the literature that it may be that TRPV1 channels are involved in food intake. So all cells have an oily biolipid membrane which contains the cell. Unfortunately, ions cannot penetrate this lipid membrane, and so there needs to be specialised structures or pores that allow the movement of ions between the inside and the outside of the cell in a controlled manner. And one of these channels is actually the TRPV1 channel, which is activated by capsaicin. And capsaicin is found in chili peppers, and that's what gives it its hot taste. And the capsaicin can activate these TRPV1 channels, allow the passage of calcium into the cell, and then change the excitability of that cell. And here you can see the response of a tension receptor to stretch in control conditions. And if we add a capsaicin, an agonist of this TRPV1 channel, older, we didn't use capsaicin in this case, you can see that we get an increase in that response. So it increases the excitability of the nerve. And in humans, there's been studies that have shown that capsaicinoid or capsinoids are a potential role for weight management. And you can see that if we treat with capsaicin-rich red pepper foods, you get a reduction in energy intake. So there is some indication that these are involved in food intake. So we've actually had a look at this channel. We were fortunate enough to have some TRPV1 knockout mice. So these are mice that have no TRPV1 channel in them. And we compared them with the TRPV1 wild type, so they have TRPV1 in them. And you can see that in the wild type mice, the same as what we saw before, you get a reduction in the response to stretch in the high-fat diet mice. In the TRPV1 knockout, so there's no TRPV1, there's no difference in the response between standard laboratory diet and high-fat diet mice. In fact, what is happening is, if we compare the standard laboratory diet between the wild type and the knockout, there's already a reduction in the response to stretch, and then there's no further reduction in high-fat diet conditions. So it's possible that these TRPV1 channels are involved in that dampened response, and it's something that we're looking into. Again, there's a correlation with the sensitivity of those afferents and the amount of food consumed. So as I said, in TRPV1 knockout mice, fed a standard laboratory diet, the mechanosensitivity, the response to stretch is significantly dampened, and that correlates to an increase in food intake. And with the mucosal receptors, we saw no difference with the high-fat diet, and there was no difference in these mice either. So we know this response is dampened, and we think it might be TRPV1 channels. We're still doing research on that. But the next question is whether we could reverse that. So we know that with the increased prevalence of overweight and obese individuals comes the increased number of individuals trying to lose weight, and it's a major industry, the weight loss business. And it's known that of the third of Americans who are obese, 50 to 70% are trying to lose weight. And reduced energy consumption is successful in losing 5 to 9% of body weight, but 35% of individuals regain their initial body weight after 1 year, and long-term maintenance is very difficult, and only about 5% of individuals actually maintain weight loss. It takes a lot of vigilance. You have to monitor your food and your exercise continually. And this is probably because the post-obese state, so the person that's lost obesity, is not physiologically the same as a person that's never been obese. There's an increased, the hormone levels are different, there's an increased desire to eat, and thus an increase in food intake, and there's a decrease in energy expenditure, which ultimately goes towards regaining weight. So are these gastric satiety signals having an impact on this in any way? So what's happening with gastric satiety signals? We also had another group of mice that we put on the high-fat diet for 12 weeks. And as I said, at 12 weeks, the response to those sensory nerves is dampened. And then we put them back onto a standard laboratory diet, and they lost a little weight in the first week, and that's because these mice loved the high-fat diet and refused to eat. They were very stubborn, refused to eat the standard laboratory diet. But we coaxed them, and then they got used to the standard laboratory diet again. They never got down to the mice that were fed a standard laboratory diet all the way through. They kind of follow along parallel for a little while, and then about at the 21, 22 week time point, they start to gain significant weight. And you can see here, this is the food intake over that period. The red is the standard laboratory diet, blue is the high-fat diet, and the green is the ones that have been put back on the standard laboratory diet. And you can see that the green follow along for the 12 weeks the high-fat diet mice, and then when they're put back on the standard laboratory diet, they go up to standard laboratory diet levels, and this is grams. Then they continue to rise, so there's a significant increase above standard laboratory diet levels, and they're actually gorging themselves. And if we look at energy, what's happening is it follows along with the high-fat diet group, obviously, for the first 12 weeks, and there's a significant drop down to standard laboratory diet levels. And then it gradually increases, and at the 24-week time point, it's almost identical in calories to what the high-fat diet mice are consuming, because you can imagine how much food they're actually eating. So they're trying to maintain the level of adiposity that they had when they were on the high-fat diet. With the mucosal receptors, if we go through this, you can see that there's no effect. And with the tension receptors, we get the reduction in mechanosensitivity in the high-fat diet group. And unfortunately, if we put them back on a standard laboratory diet for an equivalent amount of time, that reduction is maintained. So it doesn't go back to normal. We don't know if that will go back to normal if we leave it long enough, but it certainly hasn't gone back to normal on an equivalent amount of time on that high-fat diet. So is there a way of actually tricking these nerves into going back to normal? Can we change something? Can we alter something to make them the responsiveness change? And we think we found a way, so I don't want to leave you on a low note, that we can we can actually entrain those gastric satiety signals by altering food intake patterns. So I showed you in that circadian rhythm that you can influence those circadian rhythms with food intake. So if we eat at unusual times of the day, which is what those high-fat diet mice are doing, we can change an abundance of things. So what we looked at is actually feeding them either a standard laboratory diet or a high-fat diet for 4 weeks, and then for the remaining 8 weeks, restricting their food intake to either the daytime feeding or the nighttime feeding. So if we fed them a standard laboratory diet just during the light phase or just during the dark phase, then the weight changes. There is no weight change between them and the mice that have been fed ad libitum. So they seem to compensate at the other times when they have got food available. In the high-fat diet that are fed ad libitum, there's a significant increase in weight. But if we do that restricted feeding again to either the daytime or the nighttime, you can see that they lose weight. They never get down to standard laboratory diet, but it's significantly reduced compared with the mice that are fed ad libitum all the time. And then if we look at these responses to stretch, this is standard laboratory ad libitum and high-fat diet ad libitum. If we feed just during the dark phase, we get a nice circadian rhythm similar to ad libitum, because they actually feed mainly in the dark phase. We can switch that if we feed them just in the light phase, so you get a kind of a mirror image. But what's interesting is that we can get that circadian rhythm back in the high-fat diet group by feeding them just during the dark phase. And we can reverse it in the light phase. So we can reverse that reduction in mechanosensitivity by just changing feeding habits. I'm nearly finished. So tension receptor mechanosensitivity is suppressed in high-fat diet mice. It's possibly due to a disruption in TRPV1 signalling. It remains suppressed on return to a standard laboratory diet, and restricted access to a high-fat diet prevents that ablation in circadian variation, or that reduction in mechanosensitivity in gastric satiety signalling. So we might not need a pharmacotherapy, we can just change the timing of food intake. And I think I've gone over time, haven't I? So, No? Okay. So the take-home message here is that there are changes that occur in obesity that would facilitate food intake. These changes are not readily reversible and may contribute to the difficulty many people have in achieving and maintaining weight loss, but that actually it's not a total loss, and that we may be able to manipulate the sensitivity of those afferents. And I'll just briefly go through the effects of leptin, the hormone, in obesity, as I've shown you that before. So this is leptin in standard laboratory diet and high-fat diet mice. You can see in standard laboratory diet mice you get a nice increase in mechanosensitivity. This is lost in high-fat diet mice, and this is typical of what you probably would expect, because in obesity you get leptin resistance, and this is typically what we're seeing in these mucosal afferents. And then it returns partially returns in the refed group. If we look at the percentage excitation, we can see we get a nice excitation in the standard laboratory diet group. This is knocked out in the high-fat diet group, and it actually is only partially returned in the refed group. And remember that we've put them back on the normal diet for an equivalent amount of time. There's in the whole nodose ganglia, which innervates, which contains the cell bodies that innervate the whole of the body. You can see there's a slight pattern in the expression of the receptor. But using a method developed by Richard Young to trace the nerves specifically in the gastrointestinal tract back up to the nodose ganglia, we can actually leave it to trace, the tracer to trace for a few days, then dissociate the cells in the nodose ganglia, and under a fluorescent microscope we can see this is a specific gastric afferent, and we can draw around that afferent and laser capture it into an Eppendorf. This is another core facility at Samri. And if we look at, this is the whole nodose ganglia, if we look at just expression in those mucosal afferents, you can see that it clearly reflects the responses to the leptin. So this reduction in effective leptin in the high-fat diet conditions is due to a reduction in leptin expression. So with tension, we get no effect in standard laboratory diet. In high-fat diet, we get an effect that's similar to what we see in the fasted state. So the nerve is actually confused, it thinks it needs energy. And this is partly returned in the refed. It's still a reduction, but it's not as much if you look at the percentage reduction there. So the effect of leptin on gastric vagal afferent satiety signals are dependent on nutritional status. So in summary of this talk, I hope I've shown you that gastric vagal satiety signals exhibit a high degree of plasticity to finely control food intake. They respond to circadian cues, nutritional status and appetite hormones. There are changes that occur in obesity that would facilitate food intake, and these changes are not readily reversible and may contribute to the difficulty in maintaining weight loss. But I hope you appreciate that a better understanding of the mechanisms involved in gut satiety signalling will enable more effective treatments and or lifestyle strategies for obesity. And then I'd just like to acknowledge my research group. Thank you.
Thank you very much indeed. So you said that you didn't want to leave us on a low note. It wasn't going to be a low note, actually. There was one take-home message where it was, I should go home and have a curry, but yes. I'm actually not quite sure when to have it. Yeah. I also noted your league table about obesity and noted that it didn't match the Olympic league table, but no. Maybe tonight's not the time for either you or I to say anything about Olympic league tables. Time for a couple of questions, I think. Yeah, please.
Thank you. Very interesting. What will happen if you put more carbohydrates in the mix? I don't know, you got 60% fat, so was the rest carbohydrate or
yes, it's carbohydrate and protein. So it's about it's balanced as just lots of fat. Actually, we've looked at carbohydrate diet, a high carbohydrate diet, and like I was saying to you, mice are very, very fussy, and they actually, it was like fudge. It was quite sweet, and I said when the experiments began that if I was eating that, I'd be sick of it within a few weeks, if not days. And that's exactly what happened. They ate for 2 weeks. They were hyperactive, and then they just stopped eating. They wouldn't eat it anymore.
So you couldn't get the weight gain on the...
No. Perhaps a bit smarter than humans.
Thank you very much, Amanda, for a very interesting presentation. As a clinician, looking at your data, the most striking data to me, despite the great interest in the molecular that you were describing, is really the early data, which really shows we've got an enormous public health problem.
Yeah, yeah, that's right.
And this is a problem that we've really probably seen since, I guess, post-Second World War. It's from the 50s on. So So it's unlikely that any of the anatomy or our genetics has changed in that time, but something has dramatically happened to make us sort of like fat. And it would seem that it's got more to do with the way in which we've constructed society, the abundance of food that you talked about. But if we're really going to get bang for our buck, I guess there's two questions. One, what is the intervention that might come out of this? And would it likely to have really a great effect at a public health level? Or are we better off putting our money into reconstructing our societies, the way we eat, the way we don't move and don't walk and don't travel places? Are we better engineering society to get rid of this problem, or are we better off finding some sort of intervention that comes out of your work?
Yeah, I suppose, unfortunately, since post-war times, the lifestyle has dramatically changed. I mean, even in my lifetime, and I didn't see the war, thank goodness. Things have changed. I mean, when I was a child, we used to grow our own food. We used to use, it was heavy labour really, to even do the washing. The television didn't come in for a few years, and then it was a luxury that you only spent an hour, maybe, if that, watching. So there's been a dramatic change in a very, very short time, and I don't think the physiology has had time to catch up with that. And unfortunately, that's led to these physiological problems that we see here.
Physiology is not going to catch up.
No, but we can help it along.
So I think on that we'll close, and just to thank you very much. I think what you've done is a beautiful demonstration of very elegant technologies with some great systems that you've developed at SAMRI in that executive housing for the mice, and really highly skilled work, which is making a big impact on an important topic. So thank you very much indeed. Thank you. And safe home, everyone, and hopefully see you again at future meetings like this. Thanks. Great, thank you very much. I that's all right. That was very good, wasn't it? Yeah.
Thank you.
I used to study Westling, taught me respiratory virology.
Oh, did he?
5 years ago.
Yeah.
It's got a long way since then.
Thank you, thank you.
Just I kind of said something earlier on about the vagotomies and so on. I don't think obesity was a problem in post-vagotomy, but is that because they were also just, because it's quite a lot of nerves got cut, but it's also because there's a balance between ghrelin and leptin. So you were actually cutting both out.
Yeah. Thank you.
It explained why when I was an undergraduate we